But the next talk we're going to get set up here is Brooks, and I probably will be assisting talking about upstreaming CHERI to FreeBSD. So I think I need to detach.
Sure. Yeah, so I'm going to talk to, I'm Brooks Davis from SRI. I'm going to talk today about what CHERI is and about upstreaming support to FreeBSD. So what is CHERI? CHERI is a processor architectural protection model. We impose a capability system model with hardware and software and add new security primitives to the instruction set architecture. And that's implemented through a mix, and that's implemented in the CPU and the system on chip in the microarchitecture. Let's see. And from that, we can build a variety of new security behaviors. Thank you. So the target of CHERI is to bring memory safety and compartmentalization to C and C++ trusted computing bases. We can also provide benefits to managed languages and modern languages like Rust, but our focus particularly is in system software like CHERI, like a BSD operating system, hypervisors, firmware, et cetera. And so I'm going to tell you a bit more about how our implementation works, and then talk about the features we have and about upstreaming and why now is the time to upstream support for CHERI into FreeBSD. It's worth noting that there are multiple industrial implementations of CHERI. The screenshot here is a bit of Morello, the ARM Morello chip, which is a prototype architecture, and there's some others that I'll talk about later. So how does CHERI work? CHERI introduces a new hardware data type, the capability. It extends, in a 64-bit version, it extends 64-bit virtual address spaces with metadata that includes permission and bounds, as well as a tag, which is not part of the main memory and is managed by the microarchitecture. Capabilities are used for all memory accesses in a CHERI system. For things that are pure capability, that means direct manipulation of memory via dedicated instructions, so all loads are via a particular capability. There's also a legacy operating mode where we have a default data capability, so integer load and stored operations are bounded by that default capability. And there's also a program counter capability which bounds jumps and the like. Capabilities with the tag are protected with the tag. So if the tag's not valid, then you can't use the capability. And their validity is controlled via guarded manipulation, which is to say there's special instructions for doing things like reducing bounds, setting the address, et cetera. And if you don't follow the rules, so you try to increase the bounds, you lose your tag. Likewise, if you store a bunch of characters on top of the capability, that's not a capability store, so tag goes away. Now you don't have a valid pointer that you can use. So we use CHERI capabilities to implement memory safety in C and C++ programs. We replace all of your pointers with capabilities. And so, you know, any programmer visible pointer becomes a capability, and the register file contains capabilities where you would expect stacks, bills, likewise. In addition to these explicit pointers that you think about as a programmer, we also protect implicit capabilities. So your return address that's stored on your stack, vtable entries in C++, and then your GOTs and the like are also capabilities. So in a pure capability CHERI C++ application, your memory is confined to those allocations given to you by the kernel. You can't access just random bits of your address space. You can only access the bits that are part of your process, or that were given to you explicitly. So you have your program, you have your runtime linker, you load another library. Those are all separate capabilities rather than just being things laid out in memory. So in a given thread, you can think about there being a reachable set of capabilities. That's the transitive closure of whatever's in your register file at the moment. You could reach, there's a bunch of capabilities, they could reach the memory, you can load more capabilities from that memory. But that's a subset, that may be a subset of the total memory that's accessible to in your address space. And we can use that in turn to build compartmentalization with CHERI. So we take this memory safety, and on top of that, we build a strong compartmentalization model where it's possible to have multiple threads that are completely separate within a single address space. You could conceivably have a single address space operating system, in fact, with no MMU. There are some research operating systems which have done that. We're not doing that in CHERI BSD. Virtualization is, in fact, extremely useful. So we like to keep that. Whoops, I've jumped ahead. There we are. And then here's if you were, the previous diagram where we had all the registers pointed to GOTS and to stacks and all that. Well, now you have two compartments in this picture. And then we can have selective sharing with CHERI capabilities. This means that we can have extremely fast sharing. It's just loads and stores. Atomics, of course, to ensure concurrency if required. But there's no process switching. There's no context switching, or very little context switching. So we can build extremely fine-grained compartments, potentially multiple orders of magnitude more than were possible with current process-based technologies. So CHERI has been demonstrated at a wide range of scales in terms of actually building physical things. So I'm demonstrating today on a Morello box. This is an ARM Morello prototype CPU. It's got four cores based on the Neoverse N1. This is the design that's the basis for the first generation Graviton servers in AWS. So it's a, at the time, best of class superscalar core. In the middle, there's a design coming from Codasip. They're primarily an IP vendor, building CPU IP. It's sort of a mid-range application core, dual issue, like 9-stage pipeline, I think, MMU. It can run, like Morello, it can run FreeBSD, Linux, et cetera, but it's a smaller, more restrained in scope. This is something you could call them up and buy today. Obviously, you've got to fab a CPU and a SOC from there, but you can buy IP in this space. And then at the bottom, there's CHERI. It was developed originally at Microsoft by a team run by David Chisnall. They took the RV64E. This is the smallest version of RISC-V, the most stripped down. And they said, what if we put CHERI in and it's a mandatory feature and we rip out the PMP, so CHERI provides all of your memory protection, and then we take advantage of the small scale here where the amount of memory is small, so sweeping all of it is feasible, and in fact it's all on die. In normal applications, it's going to be just some SRAM, and you'll decide how much you need. And also, let's build a real-time operating system with that, assuming CHERI is a first-class thing, and assuming that we want strong compartmentalization as our core primitive of the operating system. And so they have integrated that into C language annotations and the like. So there's a whole scale of things, from tiny things to big things, and we believe the whole scale should be viable. One of the things with CHERI, unlike past capability systems, which have met with market failure or not even arrived in the market, we can run legacy applications. We can run side by side. You could take a Morello box and you can install a standard Debian image or a standard FreeBSD image on it. It just works. It does all the things you expect. You don't need to change a single bit. But if you bring CHERI in, you can, with CHERI-BSD, like in this picture, you can have an incremental deployment of pure capability software. So a pure capability kernel, pure capability window manager. Most of the applications in this picture are pure capability. And then in this example, we've got a legacy Chrome web browser and a legacy JVM. We actually have prototypes of both of those things. And depending how time goes and how people are feeling, we might try to live dangerously and show you Chromium at the very end. But we're having some integration troubles today with this particular machine. So things might get a little exciting. So if you want to learn more about CHERI later, chericpu.org takes you to our website. There's also CHERIalliance.org is the CHERI Alliance. It's a growing group of companies and organizations who are promoting CHERI, trying to work together to develop things. And of course, we have been around for about 15 years, so we've written a lot of papers. The instruction set is quite long, and so there's 1,000 pages of reading material or something if you're so inclined. CHERI, in addition to being a research thing and coming to product, is being standardized by RISC-V International. There's a CHERI special interest group and technical group, co-chaired by Alex Richardson at GChips and Simon Moore at the University of Cambridge. And they're working together with a number of companies to finalize a draft spec. It'll be RV64Y. C was already taken, so it's Y for capability E. Problem with using letters, so you run out of them. So yeah, it's on the way, currently scheduled for ratification in August. It might slip a little, but I think things seem to be generally on track. We're not seeing a lot of big delays at this point. So it's probably the biggest thing ever adopted into RISC-V, though. So it has been quite a process to figure out what the process will be to add this thing. And now, of course, part of the reason why I'm talking about upstreaming to FreeBSD is we've got real hardware coming. On this slide, I have, we have a number of application cores. These are things you can run FreeBSD on. Right now, there's stuff you can run in FPGA. There's Morello. There's a couple more things you can run in FPGA later. And then on here, these products are, I think, fairly low scale, but nonetheless cores by SetKey. And then there are a couple other tape outs that I know of that are planned for the next year, but we don't have leave to put them on here. So there will be physical hardware we can buy next year. That's the current plan. And then, in addition to these application cores, we've got some sort of large microcontrollers and then tiny Chariot microcontrollers. There are a bunch of tape outs going on there. Lots of exciting stuff happening, and some pretty cool things. So, in addition to CHERI-BSD, we of course have had to build a tool chain. So we've got a complete Clang and LLVM tool chain. It's a fork of LLVM. One problem is with all the different hardware, we also have forks of the tool chain. We're working on getting the number back down to something more manageable at the moment. But there are complete things. And then we have strong GDB support, thanks to John, and a bit of ARM and Linaro as well, adding support for all the things you'd expect from a debugger. So, and then in addition to LLVM and GDB, ARM has also produced a proof of concept port to GCC. They did it, they got Linux to compile basically, and they said, yep, it works. But at the time, they didn't want to spend the engineering effort to keep it going. So, but they did say that basically, they don't foresee any problems. There's not an obvious clash between the software architecture of GCC and capabilities. And then I guess beyond things like compilers and debuggers, for instance, Mark has a nearly working port of dtrace that is getting in the final stages of review, and we'll get that into our tree soon. So CHERI, despite the strong memory protections, it doesn't prevent the kind of debugging and diagnosis that you need, which is, I think, really important. If you have security thing that makes it impossible to debug your system, ASLR, then that's kind of problematic. So we've avoided those things. Now, a bit more about CHERI-BSD. CHERI-BSD is our main operating systems research platform. It's FreeBSD-based research operating system. We've been developing it for, I don't know, 13, 14 years now. And we've incrementally deployed CHERI into it. So we use it universally. We have, running on this system, we have a pure capability kernel, so spatial memory safety in the kernel. And then almost all of the processes running on the system, actually I think all the processes running on the system at the moment, also have full spatial memory safety, heap temporal safety, and fine-grained compartmentalization at the library level. One thing to be aware of with CHERI-BSD, though, is the compiler technology was growing along with the operating system. So many of the changes we've made are engineering artifacts of the tools we had at the time. And that's one of the things that we need to clean up on the path to upstreaming to FreeBSD. It's worth noting also that we've demonstrated that the basic things around spatial memory safety in particular, the ideas are clearly portable. ARM and Codicip have both produced, have in turn produced a user space implementation of pure capability processes, and then a pure capability kernel.
For Linux, right?
Yes, for Linux. Yeah, so these are not just things you can do on FreeBSD. They're things you can do everywhere, but FreeBSD has perhaps done more of them. So with CHERI-BSD, we have lots of good features. We have spatial and temporal memory safety for user space processes, spatial safety for the kernel. We have all the usual debugging bits that you developers expect. We build friendly installers for Morello. We have a full KDE graphics stack, which when the HDMI stuff isn't being finicky, works great. And then we also have compatibility with 64-bit legacy applications. ARM chief architect gets cranky when we say legacy, the legacy ISA, but it's true. We also, for pure capability code, we have about 10,000 ports are building, and then we also build another 26,000 memory unsafe packages. That number is probably a little lower than it should be, but we install them in a non-standard local base, and that breaks a bunch of things. So we fix things that are a problem and don't fix the rest. We have a Beehive hypervisor. We have the Beehive hypervisor working with CHERI, so you can run CHERI-BSD in Beehive. It's great for kernel development. We also run it in QEMU, which both of them give you a nice debugging experience. And then we have an experimental library compartmentalization as well as a coprocess compartmentalization that I'll mention in a bit. And it runs on all the usual things. So we run it in hardware emulation and FPGA. So we did here's the sort of the current stack of the system. A study a few years ago ported the KDE desktop stack to CHERI. This was actually done for MIPS on QEMU. The total lines of code change required was less than 0.01% lines of code, and in fact, almost all of that change was adding cross-building support to the configuration and build system. There was just a tiny bit of change in C++, and this is our experience with modern C++ that's not too disgustingly systemsy, so that we have basically no code change. And so we have a kernel. We've got DRM and Pantrost, all the libraries, all the good stuff. Yeah, I've covered the rest of this. So, oops, actually it is going to be a little bit of a demo. So I'm going to give you a little intro here, and then John's going to help me walk through a few things. Actually, let's go ahead and pull up console and do that now.
What do you want to do? first?
Let's do a uname. So here's a uname output from the system. We've got, we're running a generic Morello PeerCap kernel, which means it's, of course, a Morello generic adapted from Morello, so CHERI support, and then PeerCap means all pointers or capabilities. The other little bit is that we've added an architecture type here, AArch64C. We have a RISC-V 64C there. Let's see, let's do a procstat-a, probably through, just do a -a, and run it through more or less or whatever.
I'm a less person.
Yeah. So I guess the interesting thing here is you look in the emul line, which probably should say ABI, but it's emul. You see they're all ELF64C, which means pure capability binaries all the way through. Let's do procstat CHERI, -a CHERI. Those are all kernel processes, so they don't count. We should make them disappear. And then here we have, yes, these are pure capability processes. They're running with revocation enabled, which is to say they have temporal safety. And then this count is the number of compartments within the process. Do you want to maybe do procstat compartments on the ocular? That was bash. Well, that'll work. Yeah. So we have a basically a bit of the runtime has its own compartments. We have the bash binary. Each of the libraries is in a compartment, and then we've also have sub-library compartmentalization implemented by John, where we compile the library basically into a bunch of mini libraries. So from a linkage perspective and from a programmer perspective, it's still one thing. It all works the same, but we have a bunch of libraries inside. So in particular, we've taken I/O and we've put it in its own box. So things that link to the I/O bit have pointers into to do I/O, and things that don't link to it don't have pointers to do I/O. In some ways, more interestingly, we have this JEmalloc compartment. So we put JEmalloc in the box because JEmalloc random code getting access to those. So putting it in its own compartment protects it from the rest of libc as well as the rest of the program, and only actual malloc allocations come out. And then MRS is actually a wrapper around JEmalloc. It holds some sort of medium privileged capabilities. Yes?
So maybe I missed this, but how are allocations? Number 5. So if something's in a compartment and it wants to allocate some memory,
Yeah.
does that memory go into its own compartment? Like, how does that happen?
So if you want to allocate memory in a normal way, you'll have a God entry to pointing to malloc. So you'll make a trampoline call. You don't have to think about this at all, but you'll have linked to malloc, and therefore you can call malloc. When you call malloc, malloc returns via a register an allocation. Inside the malloc implementation, when malloc needs some more storage, it does an mmap of some big space, and then it does whatever it does to chop that up, and then it'll return bounded pointers to you. So there is some allocators are one of the things that requires the most change in the system because they actually have to do things that the C language doesn't allow you to do to, say, set bounds on things. So, yeah.
And those bounds are tied to the compartment?
No, they're not.
Oh.
They're not in any way associated with the compartment. They are.
Okay.
They are the metadata on the capability that's returned.
Got it.
And they are enforced by the hardware when you try to perform accesses via the capability.
So if a pointer wandered from one thing to the other thing could access the data in there?
Yes.
Okay.
Yes.
Which is both good and bad depending upon where you are in your current security model.
Well, it is good and bad in that the fact that you can access it is granted by the fact that you hold it.
Yep.
If you are sloppy with what you do with it, then you've given it out.
Yeah. Okay.
And there's, sort of the usual mitigations apply. You want to zero things, et cetera. And yeah.
Thank you.
So let's see. You want to do ocular?
Okay. Oh, yeah, hold on.
2349.
I need a left.
Yeah. Yeah, so this is ocular. There's a few libraries in here, a few
That's a small
compartments.
one.
Yeah, this one's not so bad. I guess we haven't put too many weird things in here. These are all dynamically loaded, so this is an interesting thing with compartmentalization. You look at some compartmentalization models, and they're very static. The reality is, when you have something like ocular or chromium, you at build time could never know what all the libraries you're going to be using are, unless you package the whole system up. There's just too much dynamism. When you update something, it may grow dependencies, et cetera. So yeah, I mean, so this here, can you go ahead and GDB ocular? And then do an rbreak ping PNG underscore or something. Slightly smaller list to be there.
I may need more help. What do you normally
Just
do?
enter. It'll just add a bazillion breakpoints.
Okay.
And then continue. You may need to go click a button or something. Yeah, click something on the menu. That usually does it. Just any menu item there. And then, yeah, do a back tray or where or whatever. Yeah, so yeah, if you look through this big call stack, you're going through a gazillion things just for some incidental PNG rendering. I think one interesting note here as we scroll down a little farther, yeah, so you'll see cross-compartment call shows up in there. We're showing where you've transitioned to compartment boundary. But otherwise, it's an ordinary stack trace. This is not, we have not turned this into a horrible distributed system.
For example, one of the things you also do, GDB knows how to interpret the code capabilities. So you don't just get the address of a pointer, you actually get the permissions and the bounds of pointers. So when you're investigating memory safety bugs, you get a little more information when you're debugging things, which is quite like, recently when I look at memory safety bugs that, what's the gentleman from MIT? Robert
Morris?
Yeah, Robert Morris submits all these lovely bug reports. And you can, like he uses ASAN often to reproduce them, and you can use ASAN, but on Morello Box, if you take down his little test applications to compile and run them, you actually get this really nice experience where you can see all the information about the buffer overflow, and you catch it sooner. You get to catch memory safety errors often at the time closer to when you screwed up, as opposed to much further later when you've trashed things and you have to kind of reverse engineer back into history of when something actually went wrong.
So let's go ahead and get out of here and let's go back to the slides. And then get on the Nginx, the Nginx, first Nginx slide. There he is, 19. And actually, I think you're in the right directory, so you could run Python 3. Oh yeah. How about you go run Python 3 in the demo.py in the background?
Live demo figuring out what we're going to do.
All right, so let's go to the slides again. You can just pull them up full screen for a minute. So this is some work by Jing Li at Cambridge in conjunction with Google. She's got a talk about KA-SAN on Saturday, but we're not going to talk about that work today. Instead, this is an Nginx challenge. It was developed for the it's a version of Nginx developed by a team at DARPA for the AI Cyber Challenge. The goal was they put a bunch of vulnerabilities in a bunch of software, and then AI was supposed to find the vulnerabilities and fix them. So they had a team of people who obviously knew memory safety because they were inserting memory safety bugs into code, and they were both reintroducing bugs and sort of adding their own. and then they produced ASAN exploits for them. They didn't know about CHERI at all. We didn't know about them. It just happened to be the case that the evaluation team for the program we're on at DARPA was also on the cyber challenge, and they said, you should look at this. So we did. So Jingli went and attacked it, and we looked at all the vulnerabilities. So it's a whole set of things, and what we found is that except for one thing where there was a feature of Nginx that requires on a feature of KQ that's only on Linux, so we couldn't run it all, we found all the bugs. We could hit them all through fuzzing or through ASAN triggers. So that's all good. And then we went farther. We kept fuzzing, and we had bonus bugs. Because it turns out that writing C code is hard. And even people who are super aware of buffer overflows, like they were contracted to add them to code, they used fuzzing in their processes, they still added extra bugs. So they added two bonus bugs, plus there was one bug where the ASAN trigger was required a full overflow of the object, because that's what ASAN can find. But Jingli's work, in her work, she believes that that vulnerability is actually exploitable without triggering ASAN, and in fact, leverageable into a full exploit chain, because it was a sub-object overflow. So that, let's see, and I'm going to go, so we deterministically mitigated 114% of the vulnerabilities added to the software. So that's the fun punchline. John, do you want to pop up the screen?
I have a question.
Yes.
So that's really cool. Just so a statement, not question. Can we use this as a way to find vulnerabilities in code that might not even run in this architecture?
Code that won't run it on it at all, no. Code that you've ported to it, which often
That's
takes...
sort of what I meant,
Which
yeah.
I will say, often takes no porting. And I'll show you, I'll talk over an example, which is the Chromium demo we'd like to have given in a bit. You can often do no porting and fix the bugs. And in this case, we just ported to CHERI. So we put bounds on the pool allocator, and we fixed a few compatibility things, which are the sort of things you have to fix with CHERI, not a lot of code changes. And that's it. We didn't try to fix any of these bugs.
That's really nice.
And in fact, you know, if you combine CHERI with fuzzing, and I think Jingli will talk about this at her talk, you potentially have the ability to find bugs at a higher rate, or more, you know, and in more interesting ways. We didn't design CHERI though to be a bug finding tool, so we're careful not to make overly strong claims about it. There are some things ASAN can do better than we can. They can do temporal safety, whereas and they find things quickly, whereas we don't always. But for instance, we're not vulnerable to bugs where we jump way out of bounds and don't hit red zones and things like that. So yeah, here's a table we regenerated in the background, the table from before. We've got 3 columns here. So we have the legacy architecture. You know, some things crashed, just running the tests. So whether the bugs were mitigated or not, I don't know. When we publish this formally at some later point, we'll know. And then here, we crashed in almost every case. We got one case where we didn't crash at all. It was a temporal safety bug. And then we had a couple cases where when we switched to a mode where we do a full revocation sweep for every free, which is very expensive. So scanning all of your memory every time you free a capability. It's not something you do in production, but it's something you could do here. Then we trigger some things earlier in that case. So let's see. Let's go ahead and flip back to the slides. And I'll talk about another grand challenge problem. So we have a prototype port of Chromium. It's still largely due to the V8 runtime. It's still not super stable. But we can render mini web pages. We can sometimes do JavaScript. We like to not do demos on the live web because if you go, you go to bbc.co.uk or something, it's fine today, and then they like put a new tracker on or something, and it uses some feature of JavaScript we haven't tested. So we tend to do canned demos with this, but we ported in about 18 staff months, we ported Chromium's 27 million lines of code and any libraries that we hadn't previously ported that were dependencies. That's another 47 million lines of code. And then we ported V8, it's about 2 million lines of code. We're not all the way there yet, but like many more tests pass than don't. And we're sort of working through the test suite. Right now we're in a bit of a funding lull, so we're not working very fast on it, but it's there. And so here's the thing, like we had basically 2 people, 1 person mostly full-time for about a year, and 1 other person on and off. So about 18 staff months. It's a lot of individual pain and suffering. But Chromium's security team is over 100 people. So this is less than 1 week of effort by Chromium's security team. And we get some pretty cool vulnerability mitigation. So here's an example. This is a demo I wanted to give, but for a variety of reasons, I won't give you this exact demo. However, this CVE, if you go to a big company who has a web browser team, they will know this CVE. You don't even need to tell them the blast part, they still wince, just looking at the number. Because this was a first-party bug that hit Google on Android and Chrome, and a second-party bug for Apple. Both Android and, so definitely iOS, and I think Android had 0 quick vulnerabilities, root exploits by nation-state actors. Super bad. This was well fuzzed. You know, they followed best practices such as they are for C and C++ development. The problem is, it was so deep in the Huffman code, the fuzzing tools didn't get to the bottom and didn't find it. So it went undiscovered for years, and then due to issues in CVE reporting, was fixed and then not found, and was like found, reported, but reported as part of some other toolkit, and so it was found over multiple years. And it was a simple buffer overflow in the Huffman code. With this, if we click on an image that exploits this bug in our Chromium test, we just get the all snap, you hit back, you're fine. If you're running an ARM64 version, silent memory corruption from a bug that's known to be a 0-day. So, and here's the thing, we didn't change a line of code in the WebP library. All we did is recompiled it. We had to change a lot of code around it, but that's super cool. That's why you want CHERI. There's a lot of it. So let's talk about upstreaming. I hope I've demonstrated that there's a lot of cool value in CHERI and that there's a platform coming. I think the requirements for upstreaming to FreeBSD, our patches are not trivial, but not too bad, I think. We've been maintaining them for a decade of fairly continuous merging. It's pretty straightforward, and we're actually going to slim them down quite a bit, so I'll talk about that. So some thoughts about upstreaming. We were thinking about upstreaming both RV64Y, that's going to be a shipping product with a lifetime, unless everything fails, but we don't think that's going to happen. There's enough product coming, and I think I hope we're going to be soon at the point where we landed enough products where there's fear of missing out and people have to start adding CHERI to their products. We also want to upstream Morello support. This would definitely be tier 3, which is to say no guarantees that anything happens, no guarantees of stability in the system. If ARM decides they want to ship a product, it won't be quite Morello, and we'll just break the API. But Morello systems are available in limited quantity, and they're fast, they make good demonstrations, and they're they're usable systems. So we want to do both to give us sort of the best of both worlds in terms of a shipping product and a demonstrable product where we can provide resources to committers.
And also, if ARM ships a future version of their architecture that has CHERI, there won't be a lot of source code changes.
Yeah.
The source code will be mostly compatible. The differences will be in things like opcode encoding that'll be kind of hidden inside the tool chain, but not necessarily a lot of churn inside of FreeBSD itself.
Yeah, I would expect there'd be a small amount of assembly change, largely because there are a few cases where, things where we've concluded there was a bug in the ISA design. There are some places where, some corner cases that no one got around to testing it, and so it got baked in, and we've had to do some minor workarounds. So we're going to focus on pure capability mode. We have a hybrid mode where we annotate selected pointers with capabilities. Has value in a number of situations, but if you apply it to the kernel, you have to annotate every pointer that might contain a user space pointer. So it's super disruptive. We have done it. We are not going to upstream it. And I'll talk more about that later. Have limited support for hybrid code and user space. It'd be a low priority. We'll absolutely support legacy 64-bit code. We have a FreeBSD 64 layer, just like FreeBSD 32, to run legacy code. And then we plan to land functionality in phases. So the first step is going to be spatial safety for both kernel and user space. And then the rest of them, we could have choices about ordering. So there's sub-object bounds, which is a higher friction variant of CHERI C, but prevents sub-object bounds disclosure or bugs. And I think we concluded that about 5% of memory vulnerabilities in the FreeBSD security advisories are sub-object. Is I think what Alfredo's numbers are.
And we currently run the kernel, and CHERI runs with this. So it's not,
Yeah.
You have to do some additional source code annotations in certain cases, and in many cases the compiler can find them for you. Some of them you find at runtime, but it's not very invasive.
Yeah, it's just not going to be the first thing we do because it's more invasive, and also there's some patterns in drivers that the compiler doesn't find, and so we find them the first time we try using the driver. So it's an adventure every time you plug in some random new PCI card. And then we've got heap temporal safety that'll come as a separate stage, even though it's very critical to a bunch of our mitigation stories because it's more disruptive to the VM system. And then we have two kinds of compartmentalization, which I'll hit on a bit more later. One of them is, I think, quite well baked, although we're still actively working on it. And the other one is parts of it are a good idea, definitely, and other parts we're not sure about. And I think, generally speaking, kernel support will lead because we should be able to run existing CHERI-BSD user space on top of the kernel, but there's quite a bit of parallelism there. So I think we'll it's okay if we don't get there all the way on the user space immediately, but we'll see. And then we have QEMU user mode for Morello today. I think Codicip is probably going to do support for RB64Y. They're going to target Linux, so we'll have to support it on CHERI-BSD and FreeBSD, but should be doable. And so that's going to be fairly essential for package building. Yes, Warner?
What version of QEMU is that based on?
Something ancient.
Okay.
Codicip has a more modern version. So we're going to have to get pulled up one way or another.
Yeah, because I'd like some help getting our stuff also moved upstream.
Yeah. And then, yeah, so I mean, I think it's important to note that, like, if you go look at the CHERI-BSD repository, the diff looks scary. Part of the reason it looks a little scary is because it has evolved over more than a decade. And like when we started out, we didn't have any compiler support beyond inline assembly for capabilities. We had little structs that we pretended were capabilities. And some of the code still looks like that in a few cases. So we're going to take a much more like straightforward and linear path to capability support in FreeBSD.
In particular, I think we intend CHERI-BSD to continue as a place where CHERI folks will do research. And if anything, we'll kind of have the equivalent of a staging clone of FreeBSD, as it were, to kind of pull out a curated history of things. And it's also true that in general, we try to upstream things that make sense already. One of the things I've been doing recently is changing various internal APIs in the kernel that actually use pointers, like various PMAP things, to use char star or void star instead of VM offset T. And when you do that, then effectively you have no diff with CHERI. And you get better type safety even on non-CHERI architectures, so making sure you're not conflating the things. And so many of those things we've been trying to do anyway.
Yeah, there's a backlog of, we merge things when we can, or when we have time while we're doing them. We try to land especially general functionality in FreeBSD first. Usually we manage, sometimes we don't.
Or when I get diffs when I'm merging upstream, then
Yeah.
it usually motivates pushing some things upstream.
Yes, when there is suffering in the merge process. Yeah, so I guess, talk about the features. So the pure capability kernel first. This is, of course, a spatially safe kernel, and with all pointers having capability bounds, or bounded capabilities. And there are some, so there's a general split of highly privileged capabilities early in boot, so we only use the one we mean to. So if you're creating a pointer to user space, you use a capability that only has access to the user address space, and the like. And then we support multiple ABIs. So we have CHERI ABI, which is the default ABI. Turns out it really has to be the default. We tried it other ways, and it was sad. It was great suffering. We have ever implemented, I think, 4 between us, maybe 5 even, compatibility ABIs over time. CHERI ABI started there, and some others. So we've got FreeBSD 64, which is basically a fork of FreeBSD 32, slightly reorganized. You could support FreeBSD 32, but there's no hardware out there that does, that has 32-bit support and CHERI at the same time on a 64-bit system.
The thing that maybe that's a little bit special about FreeBSD 64 compared to FreeBSD 32 is in FreeBSD 32, you just get to take your 32 bits and sign extend it or 0 extend it to get the 64-bit native integer pointers you have in your kernel. In CHERI, we preserve kind of whatever the user space says it wants, when oftentimes you get an integer pointer with a size, like you think of like accept or socket things that take a socket T and a socklen T. In the kernel, we then generate a bounded pointer that's used for kernel access, for copy in and copy out, so that we will actually prevent overflows in that case. So we actually give some protection in theory. We can catch a few overreads in terms of system call arguments and kind of ensure that we don't allow the kernel to be kind of contaminated with invalid arguments from user space when we can infer what the bound should be. So that's why we have a little more diff in FreeBSD 64 versus FreeBSD 32. And we currently don't support CHERI in FreeBSD 32 because we need to basically add these little annotations for, well, this pointer needs to have this length. And that's kind of the things we haven't done in FreeBSD 32 at the moment.
And ARM chose not to.
Yeah, we don't have a way to
chose not
test
to include the ARM v7 in the processor just for space and engineering reasons. And likewise, similar thing on RISC-V. So yeah, and then CHERI ABI is pure capability user space. This will come alongside the kernel. So we apply least privilege to memory access and configuration. And yeah, so every capability that you get within your user space comes from the kernel, either at startup or basically via mmap. And there's no all-powerful root capability in user space. It differs a little from the kernel in that the kernel obviously has to have access to all of the memory. But in user space, we can use the trusted relationship with the kernel to avoid that. There are some non-trivial VM changes required to do this. They're not too crazy, but there's some changes to the way the VM system works. And I gave a talk last year on the reservations mechanism that we use there. And then we require some changes to the various bits of the runtime, as well as some modest portability fixes. So, for instance, we in the original port, I think, had to change like 3 spots in OpenSSH. These days we change 0 because they've they've changed all those things. And this is really the foundation for all the other user space work. So having a spatially safe user space is the thing you need to do the rest of it. So why no limited, why limited or no hybrid support? So annotations are expensive. You have to add them everywhere and maintain them. Some work on Linux to do a hybrid kernel used the user annotation there, and it sort of works. But it's actually put in the problem is it's in the wrong place. And so it sort of works by accident. As long as there's only one asterisk, you're okay. And in CHERI-B's hybrid kernel, we chose to annotate all the user space pointers, so it's just a lot of changes. And also, our experience is that hybrid C appears to promise gradual adoption, but almost everyone who does it discovers that that was terrible. You churn your code base a ton, and you don't get much security benefit in the end. So we're just going to limit support and avoid the trap. So sub-object bounds. We've mostly done work in the kernel. There's been some work in user space. Probably actually going to remove most of those diffs, or at least not upstream them. Basically, it's incompatible with C in slightly subtle ways, and you need to annotate a bunch of things like container of use. Not very hard, and you can incrementally deploy this. So we could, for instance, do sub-object bounds on libc and make that work. But we've not looked at that. We do run it in the kernel, though. It's done as part of the pure capability porting work. Heap temporal safety. So we have augmented the architecture to make it viable to search all of memory for capabilities which have been freed. The reason you can do this is that for any capability, you can look at its base address, and that will tell you what allocation it was part of. And then we use a bitmap to indicate things that have been freed during the scan. So there's a simple check as to whether or not a pointer should be revoked. So we do a periodic scan. We have a bunch of clever VM tricks, which are mostly stable. Mark's made them much stabler. Still bugs, but so this will come along later, and we don't want to do it immediately. But it is really essential to the security narrative. Particularly strong compartmentalization depends on this. You need the ability to ensure that when you've handed something to a compartment and it says it's done, that it's actually done, and things like that. So there's a bunch of things there that need to be done. And then we have I guess, linker-based compartmentalization. So you saw, well, we had all those compartments before, 100 plus compartments in Ocular and compartments in libc. We basically reuse the library abstraction, and the initial supposition is that often library boundaries are something close to security boundaries. This is clearly false, but it is the thing we can do immediately with essentially no cost. So that's useful. What do we think? So we impose trampolines across the PLTs on PLT calls, and we separate. We have separate stacks within each compartment. So we avoid a bunch of stack leakage problems and the like. And then we have a policy language which enables non-library boundaries. So those compartments within libc, for instance, to contain powerful capabilities. And we're actively working on this under the DARPA CPM program. And yeah, here's the example of the sub-library compartments. And these are closer to actual security boundaries. There's a bunch of nuance here, some of which we're really still figuring out in terms of what the security boundaries are. Some interesting cases around, for instance, logging printfs give you some code that prints that does an fprintf to standard error. Vastly increases the power of a particular compartment. So it's something where the API is not right and needs to be corrected. And then co-process compartmentalization is another kind of compartmentalization. So Edward developed this primarily. The idea is that since you can actually have multiple processes within the same address space that are fully isolated except for an IPC mechanism. We can provide fast domain transition, probably a couple orders of magnitude faster than, say, Unix domain sockets or pipes. So really pretty cool. It's been on a side branch because it adds yet more VM complexity. And we're not totally sure which of the ideas are the right ones. I think people have successfully used it, and I think we'll eventually implement it, but definitely it's toward the end of the upstreaming process because we're not sure where it is on the research end yet. But I think a lot of people find it attractive, and we were initially motivated by things like the need to have something that has direct access to your GPU, which is highly privileged and full of bugs. And then also, need to run, access untrustworthy data. So you want to compartmentalize those things. You can't just put them in another process. So we run all sorts of things at higher privilege than we want today on phones and the like. So just a quick slide of, we're looking at contributing this. Robert told me I had to remind you of all the things many of the things we've upstreamed to the project already. So we did the RISC-V port. We added external toolchain support. The first cut of rootless builds and release and the start of releases. So much thanks to everyone who's polished all these things and making them usable within the project. But we did a lot of this stuff because we needed it in our CI environment or to allow students to work on things without giving them root on all the machines, things like that. We did the initial, Stacy's son did QEMU user mode for MIPS early on. So, a bunch of changes to the way we build system calls, libsys. And fixed a bunch of bugs as a result of our porting efforts. So, I think my favorite, ancient bug that's probably of no consequence unless, it is that you could hit tab on the T-shell command line when there was nothing there, and you would underread a buffer by a byte. Probably harmless, but you never know. And there's lots of little things. We're not finding huge security vulnerabilities generally. The code's pretty good. We're trying to poke at it. But we're seeing small things. That's hopefully an improvement. And then as John was saying earlier, we've made a bunch of API changes to sort of improve the overall code by clarifying our thinking about pointers versus integers and things like that. So conclusions. I don't know if you noticed, I should have called it out when I was talking, but a whole bunch of these features, so spatial safety, there's a Linux port, a couple Linux ports. They're not perfectly refined, but it's definitely there, and will be more production ready in the near future. Many of these things, though, no one started work, so we have a huge lead. We have temporal safety. We have compartmentalization. We have deployed subobject bounds. So we've got a chance to, be there early and demonstrate features that, people might want. And what we found in the technology access program that the UK government ran was there was some resistance at first. People were like, I want Linux, I know Linux. And then they stopped complaining about it because they didn't have a choice. And they buckled down and they did the work. They were like, this is fine. I'm not missing anything, or I'm missing this little thing, but I can work around it really easily. Not universally the case, but we have opportunities to here if we can show that we have a better product. So we hope to bring all these things to FreeBSD and ship in FreeBSD 16. I will say that, impolitically, Linux upstream taking CHERI changes is probably a 10 to 15 year, or a 5 to 10 year process. Depends on a lot of political things. There's a lot of resistance to some changes that are required. And I think we can do better. So some things to discuss. What resources is the project going to need to make this work? make sure that developers can test things when they need to, and whatnot. How do we handle releases? We're going to have an external tool chain, so we have a bootstrapping problem that we've been largely ignoring that we're going to need to solve. We have a variant of this version with package right now, but we can probably get away with putting package in the base system. Adding an extra LLVM to the tree, people probably get cranky. I would get cranky. I already maintain 20 LLVMs. What order do we merge things? So like compartmentalization and heap temporal safety, they're fairly separable. Heap temporal safety is much more intrusive than compartmentalization. It's mostly a user space feature. So what order do we want to do it in? We'll need to think about that. How do we manage patches to ports? Right now, we kind of have a, we have 400 projects in our GitHub, for like 400 repos in our GitHub, like half of which are forks of things that we've patched up, and then we add a CHERI_BSD.patch to our ports tree, and that kind of works, but it's kind of gross. So there'll be thinking to be done there. And online, we've got a sketch of a project plan. It's the one project on our custard CHERI org on GitHub. So yeah, happy to take some questions. I probably ran way too long.